This is the third section in Chapter 5, and it's a big old review on vectors. You have looked at forces, you've looked at Newton's third law, now we are going to look hard at vectors. We've talked around about them in earlier chapters, and we'll summarize it this time. The next lecture after this is a summary of Newton's three laws. So when we talk about a vector, we are not talking about a thing, it's a math technique. It's no different than it's add it to your arsenal of addition, subtraction. It's just a math technique to help you simplify and tackle some problems that look a little bit overwhelming when you start into them. If you can show your problem as vectors and either resolve or break it into components, you're pretty far away into solving that. Remember that a vector always has both magnitude and direction. So a vector is our math technique to work about things like velocity and acceleration that have a magnitude and a direction. If you don't have a direction, it is not a vector, and this does not apply. So when you're looking at something like mass or speed, it just is what it is. It's 50 grams or 50 miles per hour. It just is what it is. Vectors are only come into play when you have some direction element with it. The last thing to remember about vectors is that we can't mix them. So your displacement vectors are by themselves in a problem, or your acceleration vectors, but you wouldn't do both. If you have a problem where you need to talk about how much displacement due to some acceleration, then you go back to formulas that relate to Newton's three laws. That's how you go in between our vector quantities. So when we're doing problems with vectors, don't mix different descriptions. All right, our easiest vectors are linear. We did those almost since day one. So when I'm talking about a linear vector, I have a starting point and a direction. I have a starting point and a direction. So in this case, I've moved 4 units to the right, and then I have a second component. Say I'm moving 2 units to the right. That makes my resultant, that makes my solution, that makes my combination 6 units to the right. 4 plus 2 going in the same direction. When I talk about this, since my 2 components were to the right, my resultant is to the right. It could be up, it could be down. You need to keep track of the directions when you're solving the problem and be consistent with what the problem has asked for. But you set your own direction. All right, so this is when we've got 2 vectors in a straight line going in the same direction. What if it's 2 vectors in a straight line but going in opposite direction? Well, in this case, my resultant would be 2 to the right. If I've got 4 to the right and then 2 to the left, it comes out to be 2 to the right. All right? We did these early on in chapters 2 and 3. Now, when we are no longer linear, when we've got vectors going in at least 2 different directions, the easiest case then is when there is a right angle involved. And when there's a right angle, you can use your Pythagorean theorem. And if you remember your Pythagorean theorem, when we square the sides that are connected by the right angle and add them, it equals the square of the hypotenuse. Or you can go the other way and do some square roots. Pretty basic stuff on a calculator. If you don't remember this from earlier classes, schedule some time with me and we can review it. This should be review though now. When we are looking at vectors that are acting at a right angle, we can use that Pythagorean theorem. So let's say that I've got a case here that I move 6, I have a displacement of 6 kilometers to the north, followed by 2 kilometers to the right, or 2 more kilometers to the north, and then 2 to the right, or 6 to the right. Gosh, I can't even read what's down here. All right. If this were the case, I would I would draw the picture. I'm using colors here to help me keep track, and my resultant is going to be this value of 6 squared, and this is 6 plus 2 makes it 8. 8 squared is, all right, if I add 64 to 36, that gives me 100. And that means that the magnitude of my resultant is the square root of 100, which is 10 kilometers, because vectors are always the same magnitude. And the direction, it's not a vector unless it has a direction. So the resultant of this situation is 10 kilometers to the northeast, probably more correctly the north-northeast. So that's a very simple way to come up with a resultant when you have components. Make sure that you understand that the resultant is just the same way of saying the combination of the components. So the black vector is the same as the combination. It's a different way of stating the combination of the blue, green, and red together. You always need to draw a picture because we're not doing heavy math. A lot of times the solution to your problem will only be a picture. Try to be neat, use pencil, use color when you can, use graph paper if it helps. Keep track of your directions. Well, we just finished a situation where our component vectors were at right angles to each other. Let's look at something a little bit more complicated where our component vectors are not at a right angle. You can do this. This is similar to what we're doing. Again, keep track of your direction, draw a picture to scale, use dotted lines and colors. What we're going to do for this situation is what they call the parallelogram rule. And we have seen this briefly in class. Dotted lines will help you on this one. So what I want to do to use the parallelogram rule, I'll start with this vector F1 first, okay? And I want to draw a parallel line to F1. So this is not a vector, this is just a dotted line, okay? Does that look pretty, remember parallel lines will go on forever and never cross. So they are making a stripe right there, okay? So I've drawn a parallel line to vector F1. Let's also draw a parallel line to vector F2, okay? And I'm going to use the same gold color. I'm going to use a dotted line and that way. So the important thing to me here is the point at which these two intersect. So my resultant vector is of that approximate magnitude in that direction. And for the problems that we work, this is all the further you'll need to go. Let's have a prettier picture of that. And so my resultant, my net vector, my combination of vectors 1 and 2 is that red one in the middle. I like to keep my life a little clearer by always putting a arrow above my vector. To remind me that there is both a quantity and a magnitude and a direction, okay? And to restate, if we wanted to put numbers with this, we would have to be doing trigonometry, which makes our class entirely different. So we're not going to do that. We'll just stay with pictures, okay? So that is a circumstance where you've got two component vectors that are not at a right angle. We've looked at our two component vectors, and we have described the resultant vector. Let's get a little bit more complicated. Let's suppose that we have a resultant vector, and we want to break that into its component vectors. And these are the kinds of problems that we're going to solve in Chapter 5, is breaking out the difference between a force, usually the problems you'll have, the force is pushing or pulling an object horizontally, and there's also the force of gravity pulling the object down. Okay? You'll do the same steps, you'll do it just in a different order. And now the good news is that we are going to make our parallelogram relative to gravity, which will be a straight up and down, and horizon. So there's not, unless your problem tells you otherwise, you've got a flat surface and you're going straight up and down. So that is our frame of reference. And as I continue in my parallelogram and draw more dotted lines, I have that situation. And here it's a little bit tidier. They've told us that it's 60 degrees, that may or may not make any difference. If I want to break this into components, and if you remember your algebra, and you've got an x direction and a y direction, my components would be, I've got a component this way of that magnitude, and a component in the y direction of that magnitude. So these two components are a different way of describing that resultant. If we wanted to put numbers to it, we can go back to the Pythagorean theorem. In this case, they did put some numbers to it, and a little bit of trigonometry, and you can show yourself that the vector to the right in the x direction is 25 meters per second, and the vector going up is 43 meters per second. So what kind of problem would we see this with? You've actually seen this problem. So here's the application of the vectors, and it is when we look at instantaneous velocities, and if we're trying to deal with all these vectors that are changing directions, and in fact constantly changing direction, that gets to be too complicated. If we take these vectors and divide them into both their vertical component, which is going to be up or down, and its horizontal component, which is not changing because there's no new force acting on it that way, then we can make better sense of calculating things that are going on with motion. So our vector components are vertical and horizontal. We divide up our component into vertical. We divide up our resultant into a vertical and horizontal component that are perpendicular to each other, and we take. Now let's look at another application that we can do if we want to look at some math with vectors. In this case, we have a force. Nellie, remember, force is always a push or a pull. So Nellie is using this cable to pull the sled. All right. It gets a little awkward for us to work with that angle. So what if instead we divide our force into its component forces? So we have this one in the x direction and this one in the y direction. So it's the same total resultant force as her pulling the string, but we have divided it into two components. So when she's pulling it, which component is greater? Well, at the angle of the string that she's pulling, based on our drawing that's been done pretty much to scale, her force in the x direction, the force that she's exerting on the sled in the same direction that she's walking, is larger than the force in the y direction. Now we have avoided marking in all the other forces that are going on with this. Predominantly, what are the forces that are missing? Well, The forces that are missing are the forces in the y direction acting on the sled, which is going to be the weight of the dog combined with the weight of the sled, pulling downward based on the acceleration due to gravity, and counteracted by the normal force going upward, which is the support of the ground underneath it. Since the problem hasn't told us either that the dog levitates or that the sled sinks into the snow, we can presume that the ground can hold up the weight of the dog and the sled. Here's another example, and you'll see this several times. And this is showing how we can take ramps and gravity and the friction or the result of it, and look at how unbalanced forces will in fact give us motion. So in our first example here, we have a block of ice that is not moving. It's on a perfectly horizontal surface. Because it's ice, we can infer that there's no friction. There is the force due to gravity, which is a combination of both the mass of the block and the acceleration due to gravity pulling the block downward, and then the normal force, the support force of the surface holding the block up. All right? Now, what does not change? The thing that's constant here is the thing that doesn't change in all of this is that the mass of the block does not change, and it stays on Earth. So the acceleration due to gravity. See how the length of those four vectors is the same, and it's always pointing downward because that's what gravity does. Now our normal force, on the other hand, is always perpendicular to the surface. So as the angle of our surface changes, the direction of the normal force changes. So as our ramp gets steeper, the normal force continues to be perpendicular to it. But as the ramp gets steeper, the surface does not have to resist the motion of the block nearly as much because there's something else acting on it. If we were to, well, let's not get ahead of ourselves. The question here is that as the block is raised, does the force remain constant, and does it in fact continue to balance out the force of gravity pulling the block down? Common sense tells you this. The picture is also telling you this, that in fact as the angle of the ramp changes, the magnitude of the normal force decreases. So as the ramp changes, the magnitude decreases. And when we get to the situation of the ramp actually being at 90 degrees, there's no normal force at all. What do we call that when the only force acting on a block is the force due to gravity? Well, now we are in a situation of free fall. When there's no normal force, when there's no supporting force from the surface that you're resting on, that's the same thing as free fall. Here's our last example for this talk, and Nellie apparently has gotten rid of her dog, and now she's on a snowboard. She's still on snow or ice, which is kind of our hint that there is no friction. Our diagram shows that the force due to her weight, which is the same as her mass times acceleration of gravity, is downward, and her normal force, the supporting force from the ground, is upward. They are of equal and opposite magnitude. She is at equilibrium. From this picture, we don't know if she's at rest or if she is moving at a constant speed. But on this diagram, she has no other forces moving her in an x direction. So the mass times gravity, force that is pulling her downward, is equal and opposite to the normal force of the ground holding her up. What happens when she's on a slope? Now remember that the normal force stays perpendicular to the surface. That's by definition. Has her mass changed? No. Has the acceleration due to gravity changed? No. So her weight is the same, but because she's at an angle, her normal force is less. We're not in balance anymore, and somewhere we can split this up into component forces and show the force that is pushing her downhill. There's a change in velocity, and that is our definition of acceleration. The forces are not balanced. And in this case, if we take her weight, her normal force downward, and split it into the two vectors, she has got, and remember I do that by drawing my perpendicular lines, and then I can estimate what the magnitude of these vectors are. This one, because she's staying in contact with the ground, I know that these two are equal and opposite. So that means that there's the downhill component of this one. That is the force. It is one component of the downward force, and it's what's left over that is giving her a change in velocity to go down the hill. So it's the resultant. I'm taking the normal force away from her weight, and the resultant is giving me, or the component is giving me the force that is pushing her down the hill. So that's been your quick review of vectors. These are the kinds of problems we're going to work. Our last little lecture is a summary of Newton's 3 laws.